All right, so we're going to start off with the most common type of NMR, and this is Proton Nmr, right, or H1, right? If you think about what H1 is, it's a nucleus with just a proton, and thus we call it Proton Nmr. Hydrogen, right? This one is the most used type of NMR, and this one is really cool because it gives you a lot of information. And to acquire spectra, it takes like less than 5 minutes for the experiment. So you get a whole lot of information in an extremely short amount of time. So there's 4 main pieces of information that we can pull from an NMR. And that's the first one is the location of the peaks, right? Well, we already talked about a little bit, whether it's shielded, deshielded, upfield, downfield, that kind of thing. The number of peaks, which is going to correspond to our number of chemically different hydrogens. The area under the peaks, or the integration, which will correspond to how many hydrogens are represented by that peak, and the splitting of the peaks, which will tell us about what kind of neighboring atoms are around this hydrogen. And so here's an example of a proton NMR spectra. Just some things to point out, right? Notice the numbering, it goes from right to left, which is a little bit weird. But that's the way it happens, right? And then we've got these peaks here. You can see there's these grouping of peaks here, grouping of peaks here, and then grouping of peaks here. This red line demonstrates our integration, which will tell us about how many peaks there are. And we'll go through all of this information, right? But I just want to kind of point out the end goal. The end goal is to go from this spectra right here to the compound. In this case, it is 1-chloropropane, right? So we'll learn how to read the spectra and make sure it's 1-chloropropane. In terms of doing the NMR spectra, I'll post a little video of someone prepping a sample for NMR, but it's really quick and easy. You just take a small amount of your compound of interest, you dissolve it in what's known as deuterated solvents. And deuterated solvents mean that we have deuterium, which is H2, instead of H, right? Instead of just having 1 proton, it has 1 proton and 1 neutral. And so basically what this does, it shifts the location of the D peak. And so that way we don't see any peak from our solvent, or if we do see a peak from our solvent, it's very tiny. Because if you just used a regular solvent, you'd only see 1 giganto peak, right? And that'd be your solvent, right? So we use deuterated solvents instead, so that signal doesn't interfere. So some examples of these are like deuterated chloroform, CdCl3, right, instead of CHCl3, deuterated benzene, right, C6D6, and deuterated acetonitrile, right, instead of CH3CN, CD3CN.